So, let us start from the point where we left off. I started to talk about Glauber kinetics, and let us just take off from there. And let us try to sort of derive what, as I said, the TDGL equation from Glauber kinetics. So, that is the target, and let us see how we get into it. Okay. So, again keep in mind this sort of basic system. You have a Ising lattice, which sort of basically is a model for a ferromagnet. You have spin variables Si, which have an up component, have an up spin or a down spin. So, this is just a Z component, and Glauber kinetics randomly picks one spin and flips it to minus Si. And if you want to think in the details of the dynamics, you have to think of it being in the system being in contact. It has no intrinsic dynamics of its own. The system has to be in contact with the heat bath, which drives what's called a stochastic kinetics into it. So, that is why the choice of spin is random. Okay? And that is the important thing to keep in mind about Ising models, that they do not have an intrinsic kinetics. Okay? So, the last thing I did was the following. I am looking at a trajectory in phase space of a collection of spins. So, that is the configuration Si, which is basically a value of S1, S2 all the way up to Sn. So, as each of them can have two states, there is 2 raised to power n configurations in that phase space basically, and I am looking at a point in the phase space which is some configuration Si, and asking how the probability at that point evolves in time. Okay, and that is my what I call a master equation. So, the master equation which I wrote down is just the following, that del the probability of this configuration at time t. I need the time t because it is a non-equilibrium problem, it is not an equilibrium problem anymore. It is going to sort of evolve in two ways. One way is that if you are sitting on that configuration, if you have an ensemble sitting there, member of the ensemble sitting there, you can arbitrarily pick one of the spins and flip it. So, that is how you escape from that configuration. So, I have the probability of flipping a spin Si to minus Si, or the rate of spin flip, times the probability of being in the configuration which I am focusing on. And then, because I can escape from that configuration by flipping any of the spins, I can range from 1 to n, and that comes with a minus sign basically. Okay. So, that is called the loss term. That is the systems sitting at that point which escape away from that point in phase space. Okay. And then there is similarly a gain term from nearby configurations, which basically takes a configuration differing from this configuration by just one single spin. So, this is the configuration exactly the same as this one, except instead of Si I have minus Si. All the other spins are the same. So, that is a nearby configuration, and the probability of flipping from that guy minus Si into the configuration of interest to me. So, that is the gain term. Okay. And that is a generic form of a master equation. You always write down master equations like this. It is one of the standard tools of non-equilibrium physics. Okay. So, now so that is the evolution of the probability, and obviously the probability is going to change with time because it is a non-equilibrium process. Okay. The important sort of thing is the choice of W. Okay. And there is a sort of theorem of statistical physics. So, how do you go from a one configuration to another configuration? W must satisfy what is called a detailed balance condition, must satisfy detailed balance. So let me write down the detailed balance condition in a sort of general manner, and then I'll sort of make it more specific later. So basically, the transition probability from a configuration Si to a configuration Si prime, that's that, times the equilibrium probability of being in the state Si. So that's the left hand side. And again, I advise, I'm going to sort of give you a sort of conceptual way of thinking of it so that there's no sort of confusion about the maths in your mind, is equal to the probability of a state Si prime flipping to a state Si times the equilibrium probability of Si prime. Okay. So that's what's called the detailed balance condition. Maybe I'll put it in a box. Couple of statements about this detailed balance condition. How does it come about? Well, it comes about as follows. If the system is to be driven to equilibrium, this must be satisfied. In particular, in equilibrium, you can see that if you have a configuration Si to Si prime, the number of systems in the ensemble there, that's proportional to the probability, times the transition probability to the other configuration, equals the number of systems here times the transition probability to that, basically. Okay. So that's detailed balance. Each configuration in state space exchanging a number of systems, and that's why it's called detailed. You could also have just balance, where it doesn't work pairwise, but I need the strong condition where it works pairwise. And obviously, if the number of systems is being exchanged like that with each pair of states, the number of systems at each point remains fixed, and so the probability distribution does not evolve with time, basically. Okay. So that's why you get equilibrium. And there's a theorem which I'm not going to go into the proof of, but let me just state it for you, because it's important in non-equilibrium stat mech. And the theorem is the following, that any transition probability which satisfies detailed balance drives the system to equilibrium, Okay. And of course, it's important to know what the equilibrium ensemble is. Even if you do sort of doing a non-equilibrium problem, you need to know what your final state is. So basically, the equilibrium ensemble is where the probability is just the Boltzmann factor e raised to power minus beta, beta is of course 1 over temperature, times the h, the Hamiltonian, divided by the partition function, basically, right. That is the equilibrium probability, and I am making a very strong statement out here that any transition probability that satisfies this is going to drive this master equation to equilibrium. So ultimately, you will end up with an equilibrium ensemble. Let me at the outset say that there are obviously sort of infinite, well, if not obviously, a little thought will convince you that there is infinite possibilities for the transition probability. Okay, it's not limited to 1 or 2 or 3 choices. You can actually come up with infinite number of transition probabilities, and my theorem is telling me, and I think you should look up the proof of the theorem if you're mathematically interested, is telling me that any transition probability will drive me this ensemble to equilibrium, basically. Okay. So that's the sort of detailed balance condition, And then I am going to do a sort of look at a particular, I mean, so out of the many choices which are possible of the transition probability or the transition rate, I look at the Suzuki-Kubo probability. So that the Suzuki-Kubo form, I guess you know the name Kubo from linear response theory, right? Everybody is familiar with that. So the transition probability from a state Si, curly brackets Si, to a state curly brackets Si prime in the Suzuki-Kubo form is 1 over 2 tau s, that is just some time scale on which the process takes place, multiplied by 1 minus tan hyperbolic beta, the energy associated with that change, divided by 2. Okay. That is the transition probability according to Suzuki and Kubo, and I am just leaving it as a homework problem for you. Please do this overnight because I am still here tomorrow and day after. So, try to do this overnight and prove that Suzuki-Kubo satisfies detailed balance. If you are doing Monte Carlo simulations and using some other transition probability, say Metropolis or some such thing, please verify that those also satisfy detailed balance. It's just a few lines of calculation basically. You have to prove that that expression satisfies this. So just work out the left hand side and the right hand side. Okay. Sorry? Huh?
For Ising Hamiltonian or general?
No, this is a general statement. This is a perfectly general statement. Okay, true for any Hamiltonian whatsoever. That's why I've put it in general language out here. Okay, so just for the Glauber-Ising model, I'm considering specific transitions and a specific form of the Hamiltonian. But this statement is true in general, basically. Okay, so let's actually then calculate delta H. So now let's go back to the Ising model. So let's return to the Glauber-Ising model. Let's return to the Glauber-Ising model. And the Glauber-Ising model is basically the Hamiltonian is the Ising Hamiltonian. So H initial is equal to, so that's the configuration of it's the energy associated with Si. So that's minus J sum over nearest neighbor pairs Si Sj minus H sum over I Si, right? That's the initial configuration, and the final configuration is, so maybe I can write this in a slightly better manner. If I am going to flip the spin Si, let me just sort of isolate out the terms involving Si. So the terms involving Si are minus J Si summed over Li, which denotes the nearest neighbors of I. Okay. So if this is I, if this one guy is I, then Li denote this, this, this and this basically. Okay. So it's Si summed over Li, the nearest neighbors of I, Li minus H Si. Maybe I should use a different index actually, because I don't want you getting confused with that sum. So let's say you're flipping the spin Sk. So this is the neighbors of Lk of K minus H Sk, and then there'll be a whole host of other terms which have nothing to do with Sk, right? They're independent from Sk. So that's the initial energy. What is the final energy? Hf is equal to now Sk is flipped to, so I'm flipping Sk to minus Sk. So in that case, this becomes Jsk sum over Lk Slk plus Hsk. So basically these terms pick up a minus sign and all other terms are unchanged, right. So it's fairly easy to calculate the energy difference. The energy difference on this flip is simply delta H is equal to H final minus H initial. That's equal to, इसमें से ये subtract कर दो तो it's 2J sum over Lk, this 2J Sk sum over Lk Slk plus 2H Sk and all other terms cancel out because they are unchanged. Okay? I think calculation sort of fairly obvious, right? Huh? So that then tells me that my Suzuki-Kubo form is just tan type of that basically. Okay? So if you want, I can plug it in. The Suzuki-Kubo form as Si flips to minus Si is equal to 1 over 2 tau s. Tau s just sets a time scale of some kind for the microscopic process. 1 minus tan hyperbolic. क्या हो जाएगा? ये 2 will be cancelled, so it's tan hyperbolic beta j sk sum over Lk Slk plus beta H Sk. The 2 has just cancelled out with this factor that was there in the Suzuki-Kubo form. Huh? Yeah.
Is that a unique form of that rate? Is there any other form that?
No, that's what I said, that you have an infinite number of forms which you can take as a transition probability or the rate. As long as they satisfy the detailed balance condition, the equation will be, the system will be driven to equilibrium.
In terms of energy difference also, it is not unique.
No, this is unique. Once you have the Ising model, I've done the calculation right in front of you.
No, the rate form.
Yeah.
Form of the rate.
Yeah.
Is there any other form if we?
Which doesn't involve delta H.
Yeah. Or
I think you can have forms no, probably you can't have forms which don't involve delta H. Delta H is necessary, but there are different functions available. If you just do a Google search or you ask ChatGPT or something, they'll list out many functions. This is one of the very commonly used ones. But, and I emphasize that regardless of what transition probability you use, you will after coarse graining end up with the same partial differential equation, the time dependent Ginzburg-Landau equation. Okay? So that I want to emphasize. Okay, so let's, yeah.
Like, is there, like, can one rate this different probability transitions, like which one is more efficient to drive you towards the equilibrium? Like
No. Rate is just differing from the transition probability by factor of time, 1 over time, dimensions, that's all. It's the same thing, huh? In my understanding at least.
So, suppose I am choosing metropolis algorithm,
Yeah.
this one, and then I am asking like which one is faster, which
Oh,
one
okay. Okay, that's a good question. I don't know whether this is a systematic study of which takes you to equilibrium faster. In any case, in this set of problems, I am not interested in equilibrium. Okay, I just need to know equilibrium because I know that's the end point of my process. But I am interested in the non-equilibrium dynamics. Okay, so there's no particular benefit in driving yourself to equilibrium faster. That's what I would say. Okay, but yeah, the question you ask, I don't know whether there's a specific study whether some rates are better than other rates or not. Could be, huh? Okay. Any other questions?
Also the intermediate dynamics, like from like you want to drive the system to equilibrium, but you are interested in the part which is not equilibrium. That part could also depend on the probability transition rates, which ones you are using, or is it independent of those?
Well, again, I don't think there's a proof to this effect, but generically, most transition or all transition probabilities which satisfy detailed balance will give you the physically correct dynamics. Again, it's a question of relevant terms versus irrelevant terms. In the renormalization group, I said that if you add on extra terms to the Ising model, you're still going to end up getting the same physics at the critical point. So the understanding is something similar applies out here. Any reasonable form will differ from this one only in terms of irrelevant factors, and will give basically rise to the same physics at the coarse grained level. Okay, the details might differ, but this is long wavelength, long time physics. Okay, you're interested in large length scales and large time scales. Okay, the so-called hydrodynamic limit. So in the hydrodynamic limit, the physics is universal. That's a statement.
Sanjay, are there studies where people actually have not chosen equilibrium transition rates while looking into this non-equilibrium dynamics?
I don't think there's very many studies of that. I don't think there's very many studies of that.
Like you choose the equilibrium rates.
Yeah, because in this particular case, you are actually looking at the route to equilibrium. But of course, in active matter, there's no equilibrium. The system is intrinsically a non-equilibrium system. So even the final state is at best a steady state. It's not an equilibrium state. Huh? So there might be value to violating dropping the detailed condition, have circular balance where 3 states or 4 states can sort of exchange, or having a system that doesn't even go to steady state. You can have a system that doesn't go to steady state also. Okay. But for the moment, let's get the simple problem under our belt, which is the problem of this non-equilibrium evolution to equilibrium. Okay. Okay, so now I'm going to replace this in the master equation, and I'm going to replace this in the master equation. Maybe let me just use that side of the board first, because I still have I should make optimal use of the board. Huh? So if I replace this in the master equation, I find del P by del T. Whenever I drop the arguments are just that basically. Okay. So let's make our life a little simpler. Del P by del T is equal to minus 1 over 2 tau s, 1 over 2 tau s, sum I ranging from 1 to n, 1 minus tan hyperbolic, this expression out here, which is beta j s k sum over L k S L k plus beta h S k. So that's a Suzuki-Kubo transition, and then multiplied by the same probability. Again, the arguments are the same as out there. Okay, and then the second term is simply plus 1 over 2 tau s, sigma I equal to 1 to n. It's obvious from the expression that delta h in the case where you go from minus si to plus si is just that expression with a minus sign basically, right. So that's what I'm going to exploit. So that becomes 1 plus, because tanh is an odd function, 1 plus tanh beta j sk sum over Lk SLK plus beta h sk. okay, and that's multiplied by the probability of a slightly different state. Let me remind you what that state is. It's identical in all respects to this state, except the ith spin is flipped and then comma t. Okay. That's the master equation with the Suzuki-Kubo form. I can simplify it in a sort of a very direct manner. Basically, I recognize that Sk can be either +1 or -1. So, I can get rid of it inside the tanh and bring it out here. And similarly, I can get rid of it inside the tanh and bring it out here. Please keep in mind that this simplification only applies for the two-state Ising model. Okay? You can't do it for a three-state Ising model, etc., which are more sophisticated problems, which I'll discuss at the end if we have time. Okay? I want an evolution equation for the magnetization. So, my last step is to multiply both sides by Sk and sum over all configurations. Over all configurations. Another 10 minutes and we should be at our final equation. So, this left hand side is just going to become del Sk average by del t. So, that is left hand side is the evolution of the magnetization, and this guy is going to look a bit complicated, but it will simplify, is -1 over 2 tau s sum over all configurations, which I denote as so, and sum over all configurations means what? S1 is summed over ±1, S2 is summed over ±1, and so on and so forth. All the spins are summed over all possible states. So, that and then this factor, which is sigma I equal to 1 to n, 1 minus Sk tanh, I will only write it down for the first term, sum over Lk SLK plus beta h. So far no approximations are involved, everything is exact, times P of SI T, and this is simply the expectation value of this operator basically, right. And then the second term is plus 1 over 2 tau s, again a sum over all configurations, sum I equal to 1 to n, and the second term is simply 1 plus Sk tanh. I am not going to write the argument down again, that is just the same argument, close square brackets, and the probability of the configuration which only differs in that one spin is different, times t, and of course I sum over all configurations. So far so good, huh? Yeah. It's an odd function and Sk is just plus or minus 1. So I can just bring it out. Tanh of plus something is just plus tanh of that. Tanh of minus something is minus tanh of that. Huh? I've just used the fact that tanh of plus x is tanh of x and tanh of minus x is minus tanh of x. That's all. Okay? Any other questions at this point? Huh?
I have a question.
Now, yeah.
So, you are like doing master equation, it's a non-equilibrium statistical mechanics.
You have to speak up.
So, you are doing master equation,
Yeah.
but like how there is a temperature in your equation, I mean, it's
How is their temperature? See, the temperature comes from the fact of this expression for the transition probability. The transition probability has to depend on the temperature because the equilibrium distribution will depend on the temperature, right?
But like when I talk about temperature, like we tend to think that it's like a equilibrium physics. I mean, we can define temperature in
Okay,
equilibrium.
I see your source of confusion. You assume that the system is uniformly at the same temperature. It settles to the temperature of the heat bath. And other variables are showing their dynamics. So you're perfectly right. In general, if you have a non-equilibrium system, the definition of temperature becomes difficult. Okay? But in this case, you assume that the temperature modes are thermalized out. So you've settled to thermal equilibrium, but there's other non-equilibrium dynamics going on in the system. Okay? That's a good question. Okay? Okay, any other questions? Okay, then let's do a last bit of work. So, yeah.
Multiplying by SK on the right hand. Where is the SK there?
Where?
The master equation last.
That's a very good question. Where is the SK there? Okay. Yeah, I lost that in my simplification. Let me reinstate it. The SK basically hits this guy and this guy. It gives SK out there, and SK squared is just 1 again for the two-state Ising model, and this guy are hit by SK. This becomes SK, and okay.
So the sum is over K, right?
Huh?
The sum is over K, right?
The sum is over. No. K is just a spin I'm picking out. K is just a spin I'm picking out here to average over. Yeah. Okay, then let's get your confusion clear. What is the doubt? Huh?
The sum should be over K.
Good question. Yeah.
I think we should just use some other variable.
Yeah,
other thing.
Okay. So maybe we have to just.
No, this not this
No, the lower one you can make it
lower
S1.
one.
The lower one, right?
Average SK.
Okay, let's call it SN.
Yeah, SK.
SP or
SN. Say. Okay. So then let's get this correct again. So then you don't have an SK squared as yet, huh? So let's, yeah. Maybe I should just read. I'm going to rewrite this again. This factor. So you'll have an Sn outside. Let's do it carefully. You have an Sn outside, and here you have a 1 minus Sk, and here indeed the sum is over K. Okay? And then here you have again, I hope I've got it correct this time, Sn 1 plus Sk, that. Is that okay?
Sum over K.
Sum over K, yeah. As you can see, students, working things out on the board is sometimes harder than working them out on the paper, right? Okay, I hope we've got it all correct. So I've multiplied by Sn and summed over all configurations, and that's the equation I get. Okay, now the last little bit of algebra I'm going to do is the following. Now that I have a sum of all configurations out here, it should be sum over K here also. We had changed the nomenclature basically, right? Okay. Okay, so now in the second equation what I'm going to do is I'm going to rewrite minus Si as Si prime. Okay, what difference will that make to me? See, remember this summation out here has a summation over, again, let's call it minus Sk is written as Sk prime, okay, because we switched to K, okay. So, what difference is this going to make out here? Basically, I had a summation over S1, S2, etc. So the summation over Sk, which was plus minus 1, now becomes a summation over Sk prime, which is again plus minus 1. So it's exactly the same summation. So basically what happens is the following: this term becomes the same as that term because you have a summation outside, and the only surviving term is the k equal to n term out here basically. All other terms cancel out. Do you want me to work that out explicitly, or are you can I just write down the answer? Well, let me write down the answer, and then if we have doubts, we'll work it out. Okay. Yeah, just one minute. Yeah.
Call it a minus. No?
Yeah. So what I'm doing here is basically the following. This is a key part of the derivation, so you should follow it. You had here minus SI, and now I've summed over SI out here, right? I'm summing over all spins. So I've switched the minus SI to something I call well, I've switched the minus Sk to something I call Sk prime. I'm free to do that. And earlier I was summing over all these guys out here any case, so the sum still remains the same. Huh? So this variable is now the same as that variable. Okay? And this term is now the same as that term, except when n is equal to k. That's the only time you have a difference. Once I write down the terms, it will become sort of obvious. So this allows me a huge cancellation as follows: del Sn average by del t is equal to minus 1 over 2 tau s. I have this summation in front, and then I'm going to separate out the terms where I have Sn 1 minus Sn tanh of beta j ln sln plus beta h, right? That's the first term multiplied by the probability distribution, and the second term is now plus 1 over 2 tau s sum over all factors. I am isolating out the nth term in the sum. So that's Sn 1 plus Sn tanh well, I've switched beta j lk slk plus beta h, and then you have the probability distribution. That's what I've done. All the other terms have cancelled out basically. Okay. And of course, because I switched minus Sn to plus Sn, you get a minus factor here also. Plus, there is a large cancellation of terms. Okay, I mean, I've not gone through every single line of algebra. You should do this maybe at home because, as I said, it's easier to do it on paper. But that expression was perfectly okay. So what I've done is here I've switched minus Sk to Sk prime. The summation remains the same, and there's a large scale cancel, and you pick up an extra minus sign out here. So there's a large scale cancellation of terms except when k is equal to n. Okay. Please work out, just do the cross the I, whatever, dot the i's and cross the t's, and you will get that answer basically. Okay.
Just write that also as sum over ln.
Which one?
The second one.
Yeah. Okay. That should be sum over n. Now I can take the Sn inside as I had done earlier. Now it's correct. Now I get Sn minus Sn squared, which is 1, and here I get Sn plus that. Okay. almost there. We are actually at the last step of the calculation basically. So, this tells me that del Sn over del t is equal to, basically I just absorb the time into the tau s into the time scale. I combine these two terms and I get minus Sn average plus average of tanh, sorry, this should have also been a minus sign here actually, because I switched the signs out there, right. So, that is tanh beta j sum over ln s ln plus beta h expectation value. That is the final equation. Okay. No approximations here. As yet, and I absorb the tau s into the time factor out there. So, now it is a dimensionless time. Okay. I do urge you to just sort of go over the steps once when you get home, but I think basically we have sort of figured out all the indices now. Okay. So, now this is an equation, I mean I do not know whether you have encountered this kind of equations before, but it is not great use as an equation. Why is that? It is not a great use as an equation because you have the expectation value of tanh. If you expand tanh, you will have powers of SLN, higher powers of SLN, etc., etc. So, you are going to have a coupled hierarchy of equations. Then you will have to write down another equation for Sn squared, another equation for Sn cubed, etc. And you will have a coupled hierarchy of equations which are intractable. Okay. So, this is where you invoke the mean field approximation in the dynamic mean field theory. So, you invoke mean field approximation, and the mean field approximation is a brutal one, but basically gives a closed form equation. Basically, you say that the expectation value of this horrible function is tanh of the expectation value of that. Okay. That is the mean field approximation. I am neglecting all higher correlations. So, the equation is del Sn over del t is equal to minus Sn average plus tanh of beta j ln S ln average plus beta h. Now, you have a closed order equation for the magnetization. Of course, you have this function tanh out there. Why do I call this the mean field equation? Because if you look at the static solution, you get the mean field equilibrium. Okay. If you look at the static solution, you set del by del t equal to 0, then you get the equilibrium solution, which is Sn in equilibrium is equal to tanh beta j sum over ln S ln in equilibrium plus beta h. That is the equilibrium solution, and that just 1 minute, and that of course you recognize as the earlier mean field equation, which I had written down to obtain the phase diagram of the ferromagnet. Yes. Huh? The tau s I have taken into time here. Okay. I just absorbed it into time to save myself the trouble of writing it basically. Okay. I mean, you could have done it from the very beginning by just removing the tau s from there. Okay. If you look for the static solution, that is the equilibrium solution, you set del by del t equal to 0. Okay. So, drop that term, and in equilibrium you get this is equal to this, and I put the superscript equilibrium so that there is no confusion. So it gives the correct mean field equilibrium. Okay. Any questions at this point, or can I proceed?
Why this is a good approximation, and why this is a good approximation, this mean field approximation?
Why do you do it? See, if you look at the original equation, this is exact, huh? But it's not a single equation. Why? Because if you expand time hyperbolic, then you get all factors. When you expand time hyperbolic as a Taylor expansion, you will get factors of SLN, then you will get factors of SLN squared, cubed, etc., etc. Okay, so you will have this expression is actually the expectation value of SLN plus the expectation value of SLN squared plus the expectation value of SLN cubed, and so on and so forth. Okay, so you will have to write down corresponding equations for time evolution of Sn squared, Sn cubed, Sn fourth, and so on and so forth. So essentially this equation is equivalent to an infinite hierarchy of evolution equations. Okay, and this truncation is a pretty standard one. You neglect all the higher power correlations and just take this expectation value inside the bracket. It's a first approximation. Okay, it's I mean, that's why I made a point of telling you that there are no approximations involved at this point, but now I have a mean field approximation invoked. Why do I call it a mean field approximation? In the dynamical context, there is nothing like a mean field approximation. I call it a mean field approximation because the static solution is the correct mean field solution, basically. Okay. Any other questions?
So is it that it's actually exact as the Ln numbers of neighbors for infinity or which?
No.
Why do you
This
call
is
it
never
mean
exact.
field?
Huh?
When you say mean field,
Okay, that's what I call it mean field because it gives the correct static mean field solution. That's it. Basically. Yeah. Now this equation is never correct as such.
so there is no 1 over
Number of neighbor dimension expansion or something. No. So this is going from there to there is an approximation. Okay. Probably if you have long range interactions and all, that's a better approximation as in the static case. But for nearest neighbor interactions, it's not a good approximation. Okay, so that now completes my treatment of the Glauber-Ising model. Let us now coarse grain this equation and get what's called the time dependent Ginzburg-Landau model. Okay, that will be my next section. So this is now section 3, the time dependent Ginzburg Landau model, often known as in the literature as the TDGL model, and in the language of Halperin and Hohenberg, it's model A. Is everybody familiar with the Landau free energies in phase transition theory? You remember that Landau wrote down coarse grained free energy, just assuming very simple things, the symmetries of the system, analyticity, and so on and so forth. Huh? That's the famous Landau theory of phase transitions. And then Ginzburg I think was Landau's student, he introduced this, okay, so maybe I should remind you of the Ginzburg, the simplest form of the Ginzburg, of the Landau theory. You write the Landau theory down for a ferromagnet and the free energy G as a function of psi, well, first it's a function of psi, is equal to, let's get this correct, I think it's T minus Tc divided by 2 psi squared, that's a plus sign out there, plus some constant, let's call that B psi fourth. That's the basic Ginzburg-Landau expansion for the free energy of the magnet. Has everybody seen that? Huh? And it has the sort of following famous property that if you plot this free energy, if you plot G psi as a function of psi, then above the critical temperature this is constant, this is positive. So, it has a bell shaped sort of this thing, that is for T greater than Tc, okay. And below the critical temperature it develops this famous double well structure as so, because now this is a negative sign, okay. So, and this goes under all kinds of names in the literature, the most standard one being spontaneous symmetry breaking, okay. So, above the critical temperature you sit there, psi order parameter psi is equal to 0, that is the paramagnetic state, and below the critical temperature you go from there to either of these two solutions, which are now magnetized states, one magnetized negative, one magnetized positive, okay. And basically schematically you can think of the following, that this initial condition sliding down into these two competing minima is the kinetics of phase transitions, as a matter of fact. That is what I am hoping to describe. Huh? Where does Landau come in? Landau said that I will, Ginzburg said that I will replace this magnetization by a space dependent magnetization, psi r, okay. And then you write down the free energy. Now it is a functional of psi is equal to integral over dr T minus Tc over 2 psi squared, now psi is a function of r, plus B psi 4. So, that is the Landau expression, and then he added on the following extra term, half k grad psi squared, okay. And what does this extra term do? The extra term penalizes interfaces, okay. So, wherever there are sharp gradients of psi, that increases the free energy, and so basically this whole energy is called the Ginzburg-Landau free energy. And of course, Ginzburg-Landau also allowed for this free energy to be a vector or like a wave function, and came up with a beautiful model of superconductivity using the Ginzburg-Landau free energy, right, which was a phenomenological description of what BCS had already discovered at a microscopic level. This is all physics history which you should have at least some understanding of, basically, okay. So, that is called the Ginzburg-Landau free energy. Now, I am going to take the next step, I am going to go to a kinetic version of the Ginzburg-Landau free energy, a time dependent version, and I am going to, it is called the time, naturally enough, the time dependent Ginzburg-Landau model, okay. So, basically what you do is the following, I have a discrete dynamical equations for some magnetization which is defined on a site Sn, okay, that is that. So, I have these discrete lattice sites and I have variables described on that. I do my usual coarse graining procedure. I assume that the length scale I am looking at is much larger than the microscopic length scale, the lattice spacing, and I can replace Sn by a field psi r, and in this case it will also depend on time because it is a non-equilibrium problem. Okay. So, I am going to show you how to get that from my Glauber kinetic equation. Okay. So, how you do that is the following. Again, what you do is, so I have identified, as I said, Sn I have identified as a space time dependent field psi r t. Okay. The important factor I have to focus on is this one out here. Okay. So, that is the important factor that I have, that is sigma ln SLN average, that is equal to, if that is n, then ln's are these sites here, here, here and here. So, let me label those just for convenience as 1, 2, 3 and 4. Okay. So, basically if that is the thing, then the sum over the nearest neighbors is psi, let's write this down carefully, x plus a, where a is the lattice spacing, t, plus psi, I also need a y in 2 dimensions, t, plus psi x minus a y t. Okay. That is one pair of nearest neighbors. The next one is plus psi x y plus a t plus psi x y minus a t, and so on and so forth. For each dimension you have 2 neighbors basically, right? Is that okay? That is the expression out here, SLN. Okay. Now, I am going to Taylor expand these guys. I am just going to do, so there will be as many dimensions, that many such pairs of terms. Okay. Now, I am just going to Taylor expand the first guy and leave the others to your, it will be obvious what the others should be. So, the first term is psi xyt plus psi xy, well, let me write down the following way, psi plus a del psi by del x, I am just doing a Taylor expansion, plus a squared by 2 del 2 psi by del x squared plus higher order terms, that is that one. Okay. And the second term is obviously plus psi minus, because I have x minus a, minus a del psi by del x plus a squared by 2 del 2 psi by del x squared, etc. And each of the terms will pairwise Taylor expand as so. Okay. So, it is obvious what the sort of structure of the emergent equation is basically. The odd terms will cancel out, and basically I am going to get these 2 terms combined to give 2 psi plus a squared, ये दोनों combine हो जाएगा, del 2 psi by del x squared, the first order derivative is gone, plus higher order terms. Okay. And similarly, the second term, this pair will give 2 psi plus a squared del 2 psi over del y squared plus higher order terms. Okay. Is the structure obvious? Huh? So now I'm just going to sort of combine these and get my final, not my final, but my dynamical equation. In coarse-grained language, it's del psi by del t is equal to, the first term is minus psi and the second term is tan hyperbolic. What is it? Beta j times this thing. So, each dimension will give 2 psi. So, in all this will be 2 d beta j psi, correct? And 2d is of course just the coordination number. So, let me write it as a coordination number q beta j. I hope I have got it correct. Yeah. And the second term plus beta j a squared grad squared psi plus higher order terms plus beta h. I have just basically coarse-grained this equation. I see some puzzled faces. Maybe we can stop for 2 minutes and take any queries if there are. Yeah.
Say this coarse-grained because we are relating n to r. And we are assuming r is continuous.
Yeah. And I am assuming that this material, that these variable which was defined on a lattice is now a function of space which varies smoothly. Basically, that's the usual coarse graining procedure. Okay. Is the Taylor expansion clear? Any other questions at this point?
Del psi 0.
Huh?
Del psi 0.
Sorry, have I missed something?
No, you haven't. Just that Taylor expansion has a del psi, which is 0.
Yeah, but the even that term and that term were different signs, so they cancelled out basically. The odd terms cancel out, the third derivative cancels out. Every odd term picks up a minus sign, plus minus sign. And of course, the even terms square up and so they don't cancel out. So you finally left with this gradient of the Laplacian.
But the a should be tends to 0, right? Then? The a, length scale a, now tends to 0 because we are taking.
Well, I mean, yeah. Basically, you just absorb the a into the length scale. It doesn't go to 0. Okay.
Because we are talking about coarse-grained pictures.
Yeah, but what you're saying is you're working on a much larger length scale than the microscopic length scale. Okay. So you absorb, you have a factor of a, which is some microscopic number, and like I had absorbed tau s into time, I can absorb a into the length scale. Yeah. Don't worry too much about these microscopic scales. We are interested in, again I reiterate, long wavelength, long time phenomena. Okay. Always keep that in the back of your mind. Any other questions? Yeah, please.
So, actually, if you keep for this for example, as next nearest neighbor interaction in the Ising.
Yeah.
I mean, if you do the continuum approximation, would you generate del square psi the whole square terms like that?
Yeah, you could get higher terms like that indeed. Yeah. I mean, and
so I asked because the Ising model with the next nearest neighbor has this kind of Lipschitz.
has more complicated critical phenomena.
That's a competition between del square and del square. Square.
So that actually, if you include next nearest neighbors or some such thing, you will get more complicated expansions. That's, it's all in the same framework. Yeah, basically. I'm just working it out on the board for the simplest free energy. Okay. Yeah. Any more questions?
Somewhat side comment. Maybe I'll ask. Is this not even exact on like Bethe lattices?
Yeah, probably you can find some lattice on which it's exact, So people, this is a slightly confusing nomenclature. People normally call these, I mean the people who look at these kind of things as a dynamical mean field model. But of course in condense in strongly correlated electrons, there's something else called a dynamical mean field theory, which I think you're an expert on, right? Yeah. So that's a nomenclature. It's probably exact on some form of lattices, yeah. Okay. But again, okay. So I mean, this actually brings about a good point, which I should emphasize for the students. I prefer to describe this as a motivation of the coarse-grained equation rather than as a derivation. Okay. There are too many approximations involved. So you were exact till here, but then you made a sort of brutal approximation out there, and now I'm going to make a couple more brutal approximations as a matter of fact, huh? So it's a derivation in quotes. As similarly, this Landau free energy is justifiable only near the critical point. Okay, but once you write it down, you use it all over the place, far from the critical point also. Okay, but strictly speaking, the expansions I am doing are justifiable only near the critical point, in the spirit that the Landau free energy was only made sense near the critical point. Okay, so rather than derive, or you can use the word derive in quotes, or maybe when I write on this stuff, I use the term motivate. That's a better this thing. Okay, okay. So let's do the last bit of approximations and take it into the continuum form. If I, yeah, let me make sure I've got all the terms correct. Yeah. So the last, oh, I need another page of my notes. So I'm doing all this effort to get an evolution equation for non-conserved order parameter evolution, and the long term goal is to then sort of treat that analytically using the domain boundaries. That's a sort of long term goal. Okay. So the last bit of approximation you do is the following. You Taylor expand tanh x. It's an odd function, and it's pretty easy to figure out that the Taylor expansion is x minus x cube by 3 plus higher order terms. Okay. So that's the Taylor expansion one does. So that's equal to, this becomes equal to minus psi plus x is just q beta j psi plus beta j a squared grad squared psi plus beta h plus higher order terms. Okay. And then the second term is minus 1/3 and q beta j psi plus beta j a squared grad squared psi plus beta h plus higher order terms raised to the power 3. Okay. Ugly, huh? Plus higher order terms in the expansion, huh? This is the derivation, I should have said this, this is the derivation done by Suzuki and Kubo of the TDGL equation, okay, of motivating the TDGL equation, okay. Then they have some arguments about power counting, etc. Basically, you can guess what they do, they just retain the q beta j term from that one, okay. They claim that the others are, I mean, I don't find these arguments very sort of convincing, but near the critical point they do power counting and sort of neglect most of the terms in this expansion. And the final equation Suzuki and Kubo end up with is the following. Del psi by, this remember depends on space and time, del psi by del t is equal to, let's combine terms. First let's combine the linear term, is q beta j minus 1 times psi minus 1/3 q beta j cubed psi cubed. Okay, that's from the cubic expansion, plus beta j a squared grad squared psi, okay, plus other terms which are lower in power counting, basically. The original paper actually has these arguments, okay. But I obviously am not writing down the terms which they don't care about. Remember that Qj is the mean field critical temperature. So this is Tc by T minus 1 psi minus Tc by T cubed 1/3 psi cubed plus beta j, just absorb the a into the length scale, grad squared psi plus higher order terms, okay. That's my final equation of phase ordering dynamics with the non-conserved order parameter, and that's what's called the time dependent Ginzburg Landau equation. Yeah, I don't think either Landau or Ginzburg worried about non-equilibrium phenomena, but somehow historically and correct, huh?
All the H terms dropped out.
No, the H terms are still there, sorry. I should put the H terms in, yeah. Plus beta H. Yeah, sorry. Okay.
From that, you still get a linear in psi. You know, you get something like beta h squared times psi. Yeah.
Well, if you do the power counting, you take del square.
The first
Yeah.
yeah, just q beta j psi, a single power of that and two powers of beta.
Of H. But then close to the critical point, H is,
Yeah, that's what I was asking.
H squared is much less than H.
Oh, it's also power counting in H, not
Yeah.
just in psi.
So you have the critical point in the TH space and you count in distance T minus Tc, H minus Hc, basically.
And how about that psi and rad square psi?
Huh?
Psi and rad square psi.
So each,
psi and rad square psi square.
yeah, so each of these terms is down by a factor of the correlation length.
That's good. You just drop by power counting and momentum, long way.
Yes, except they keep the first grad square term, right? Yeah. So I mean, that's what I'm saying. It's a motivation. That's a correct description. Yeah. I want the students to be very clear on that. That this is not a very rigorous derivation by any means. Yeah.
Is it somehow close to the critical point? This one is.
It's justified close to the critical point, precisely as that is justified close to the critical point. But just as with the static free energy, we will finally use this equation for far from equilibrium phenomena. Yeah. Yeah.
Explain about the power counting.
Huh?
Power counting one second. Wait, I didn't get the part like where tangent from here to there.
The power counting is basically the following. Each grad term in the denominator involves a length. The physical length is the correlation length psi, which diverges to infinity at the critical point. So that's then one, and then the other point is that h. You neglect h squared compared to h, because if you have a small quantity, the lowest power is the most important. Yeah. I mean, maybe just go back to hostel and sort of work it out carefully and convince yourself. If you can't, we'll wrestle with it again tomorrow. But yeah, both Suzuki and Kubo are very sort of venerated names in non-equilibrium physics. Yeah. Okay. Huh?
There's a psi cube, but
The psi cubed is from here.
yeah, but the Ginzburg Landau is psi cube.
Okay. This is a time dependent Ginzburg Landau. I'll just connect it to that one in a minute. Okay. They're the same. I mean, they're the same. This is just a derivative of that one, basically. The right hand side is just a derivative of that one. Yeah.
And psi square h is also small.
Psi
Square h.
Yeah. Okay.
That's
Psi is t minus tc, right? It goes to 0 at the critical point.
But we're retaining psi cube, no? So the psi square h is somewhat small.
As I said, there's a little sort of jugglery involved out here. Without the psi cube term, it would make sense for reasons that you'll see shortly. Basically, without psi cubed, the solution grows exponentially. So you need a nonlinear saturative, saturative nonlinearity, as it's called in studies of pattern formation. Yeah.
the site has length scale associated with it.
Psi is not a length scale associated with it. The gradient of psi does.
But why are we neglecting the higher order powers of psi? Like only 5 cube is psi cube is that, but power like 6 and other things.
Well, any other will have behave by this factor or this factor, right? Huh? Oh, you have q beta j psi, but psi also goes as t minus tc. Because near the critical point, I mean, if you've done this expansion, you know that the second order phase transition has, I mean, the order parameter grows continuously from 0 and it has a t minus tc form. Okay.
Sir, psi minus psi symmetry also.
Yeah, that's there in the original Landau free
Then you
energy.
neglect psi square h.
Huh?
Then you neglect psi square h from that sort of.
So I mean, there's a psi minus psi symmetry in there. Except when you turn on the magnetic field, then you break it. Yeah. Okay. Any other questions? Okay. So let's study now. Okay. I have about 20 minutes. We started 2:30, right? Yeah. And we've had questions as we go along. So I guess I can go up to about 4 hopefully. Yeah. I hope that won't be too much. Okay. Okay, we'll go on for another 10 minutes or so. But I want to give you a couple of other very instructive, no please, yeah. I want to give you another couple pretty instructive sort of ways of understanding this equation. And so I should say already that this is a TDGL equation and it describes the ordering kinetics or the kinetics of phase transitions, kinetics of a ferromagnet.
The right hand side is the dx by d side.
Sorry?
The right hand side
Yeah.
is dx by d side. Take down the GL free energy.
Yeah, that's exactly the interpretation I was going to give you next. Huh? So, this is an equivalent statement, that's the statement I'm going to make, that the TDGL equation is the dissipative relaxation of a ferromagnet to its free energy minimum, exactly as has been pointed out, to its free energy minimum. Okay. So again, I mean, you recall if you have a particle, if you have some one-dimensional particle moving in some kind of potential Vx, then you write down the sort of equation for this particle as mx double dot is equal to minus del v by del x, right? That's just Newton's law of motion basically, del v by del x. And if you include a dissipative term, you also put in minus, you put the minus friction coefficient x dot. Okay. So that's a term proportional to the velocity. We've all done this, right? Damped pendulum or something. That's the usual Newton's equation term, and that's the damped term. So in the overdamped limit, which is the sort of models people use in non-equilibrium physics, you drop the inertial term, you assume it's negligible compared to the dissipative term, and write down the model psi x dot is equal to minus del v by del x. I am presuming everybody has seen that model, yes or no? Everybody has seen that? I mean, that's when you write down Brownian motion, etc., that's the sort of model you write down. Okay. So this is exactly that model, except this is for a field. This is del psi by del t is equal to minus gamma del g psi divided by del psi, where psi is a field, plus a noise term, theta r as a function of t. Okay. So basically, you've dropped the inertial term. Friction is just that's 1 over friction constant, and that's the dissipative relaxation to the free energy minimum. Okay, and the free energy is just that Ginzburg Landau free energy out there. I hope everybody is comfortable with doing functional derivatives. It's obvious, it's just like a normal derivative for the first two terms, and then you have to work a little harder on the grad square psi term, but it's very straightforward. So basically, you can interpret the Ginzburg Landau equation that's alternative and possibly more sort of simple way of understanding how it comes about. So basically what this equation is going to do is the following. You start off from any configuration psi, okay, and that's going to evolve in such a manner under this equation to reach the free energy minimum, which is the equilibrium position. Okay. So ultimately you will end up at the minimum of G psi basically. What is? Theta is noise. In Brownian motion you have noise. Okay. So that's just a noise term. Again, when you write down your Brownian motion model, you could have some theta t or something, right? And this is usually Gaussian white noise and its simplest properties. Yeah, just the usual Gaussian process. Okay. So that's the partial differential equation counterpart of this model. Okay. Okay, I think the next thing I want to do, but maybe I should do this tomorrow, because we still have to, again we have to get into some sort of calculations on the board. I am going to take this equation, I am going to scale it into a dimensionless form, and the dimensionless form will be the one I use to do my calculations with. Okay. So that's I think this is probably a good place to stop for today. People have also heard me for almost 2.5 hours or more, and tomorrow we will proceed on with actually trying to make sense out of what we get out of this equation. Okay, now that we have an equation, we can't solve it exactly, but what sort of approximate statements can we make? Can we get the growth laws? Can we get the correlation function, etc.? That's going to be my next target, yeah. Okay, I can take a last few questions if there are any, and then we'll go into this tomorrow morning. Yeah.
In the integral equation, the grad squared translated the difference between squared the grad square.
Yeah.
Is
See, this one is just written down phenomenologically. Okay. So this is the equation I'm going to use to actually, I'm going to do the functional derivative tomorrow. Write down the equation using this free energy. Okay. And if you want to make an identification, K can be identified with this factor out here and B can be identified with that factor out there. Okay. But the derivation is so loose that identification is also not a serious one. I mean, a better way of thinking of it is just as a phenomenological equation which drives the free energy to the minimum of its minimum. That's all. Okay. So I mean, it's I don't know when you do StatMech, you've done this Bragg-Williams you've done the Bragg-Williams approximation. You can expand the Bragg-Williams term to give such a free energy. Okay, you can expand the entropy term to get this free energy, but and thereby you can give microscopic meaning to these parameters, huh? But perhaps it's just better to say that phenomenologically, just go the way Landau did and say that I'm not going to invoke any microscopic description. I am just going to sort of write this down from symmetry principles. Okay. Of course, it is important to invoke a microscopic description in the following sense that, at least in this context, that many studies of these systems are done with kineticizing models. So, you should know what the kineticizing model is about. You should also know that by some process of motivation, you can derive the TDGL equation from it. That's the point, yeah. Okay. But you could just now think that we started a new chapter. I'm going to sort of just phenomenologically write that down. And with phenomenology, as Landau showed, it's as good as it works. I mean, so if you can describe a duck and you write down some model for a duck and the duck walks, quacks, etc., then it must be a good model, right? Very respectable way of doing things, by the way. It's not, yeah. I mean, especially in liquid crystals, that's where you probably get the most fancy liquid, the Ginzburg Landau free energies. The order parameter is a tensor in that case. It's a matrix, essentially a matrix, huh? And you can write down these free energies. And there's this famous book by Ginzburg, The Physics of Liquid Crystals, and just out of symmetry, they sort of tell you कि यही terms हो सकते हैं इस order expansion पे, etc. It's art probably. Okay. Okay. Any more questions?
Can I have one?
Of course, please. Yeah.
Sorry. So in the beginning, you started with the detailed balance.
Yeah.
You started out by considering the process where it goes from SI from the initial configuration into the state with one lift.
Yeah.
And then go back from that state, the earlier one, by considering the state, initial
close one state,
one
with the flip spin, and then go back to that. Yeah.
Okay. So there, when you sort of actually wrote down the transition probability,
yeah,
it sort of depended on SL, SN, or on non-local. I mean, there was some SK.
Yeah, the neighbors of N.
SL,
right,
where L were the neighbors of K.
Yeah. Yeah.
So, and subsequently at the end, you did a mean field approximation.
I post-graded that sum and wrote it down as an order parameter plus a gradient, plus a Laplacian of the order parameter.
Okay, so I'm sort of, so physically, if I sort of think physically, the effect of flipping one spin in a kind of finite region with some short range order,
yeah,
the effect should depend on the pair fair probability as well?
Well, that's actually a very useful question. The way you think of it is the following. See, ultimately you have these domains of plus and minus. Huh? Correct? So, in the bulk you never flip spins because there's too much energy barrier for that. Huh? Where you flip is at the interfaces. So, the flipping of the spin is because somewhere the interface maybe you have two neighbors up, two neighbors down, and therefore there is no barrier to flipping. Okay. So, the flipping essentially happens at the interfaces, and it's like the interface is doing a random walk. In the process of doing a random walk, they sort of collide with other interfaces and the domains merge. So, that is how the growth process takes place, and that is why you will find out that the length scale is t raised to power half with time of these domains. So, the spin flips in the pictures I showed you happens at the interfaces basically and drives the domain growth process thereby. For conserved order parameter, it's more difficult. This is all these statements for the non-conserved order parameter. Because for the conserved order parameter, you can't have a spin freely flip at the interface. You have to have a spin on this side interchange with a spin on the other side, so as to conserve the composition.
I mean, the case where you consider
Nearest neighbor pairs. Yeah.
Okay.
Yeah. Switching, exchanging a pair.
Exchanging.
A pair, yeah.
Right.
Basically. Okay, so tomorrow I'll start off with a 5-minute summary of where we are. I mean, what all we've covered today. And if you have any questions, I'll answer those also. And then we'll go on to actually make some sense out of these equations and try to sort of actually extract meaningful results like growth laws, etc., out of these equations. Okay, thanks.